In the previous video, we studied the harmonic series, which is a series given by the sum from n equals 1 to infinity of 1 over n. In this video, we're going to take a look at this other one, which is the sum from n equals 1 to infinity of 1 over n squared. It looks very, very similar. So we're wondering whether this one is convergent or divergent. It looks a lot like the harmonic series, which was divergent. But at the same time, 1 over n squared goes to 0 a lot faster than 1 over n. So maybe there is hope. Maybe they are not going to adapt to really end up like being infinite. Actually, this is going to be the case. We just need to find a way to prove it. Again, we only have right now the definition at our disposal, so we'll just have to use that. So that means we need to go write this down, and we're going to look at the sequence of partial sums. This is a series with non-negative terms, so we know that the partial sums, the sequence of partial sums, is increasing. So if I want to see that is convergent, all I need to do is show that my sequence of partial sums is bounded. So that's what we're going to do. And we're going to take a look at some of these partial sums, some of the special ones like we did for the harmonic series, the ones that are easier to work with, and then we'll see how we go from there. Let's do, so if we take a look at the first two terms only, well, we have 1 plus 1 over 2 squared. Each term is less than or equal to 1. This whole thing is less than 1 plus 1. And now I'm going to look at S4. So the first four terms of my series. So we have 1 plus 1 over 2 squared, plus 1 over 3 squared, plus 1 over 4 squared. And the last two I put in parentheses because you see, 1 over 3 squared is less than 1 over 2 squared. And 1 over 4 squared is less than 1 over 2 squared. So then I can use these to bound my sum by 1 plus 1 plus 1 over 2 squared plus 1 over 2 squared. So I have 2 times 1 over 2 squared. That gives me 1 over 2. So I can bound these by 1 plus 1 plus 1 over 2. Good. Now let's take a look at the next partial sum that is given by a power of 2. So that's 8. So we're looking at the next four terms. So the first we have 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared up to 1 over 8 squared. The first parenthesis we already know how to handle. We did it in the S4 case. So this one here, we have this is less than 1 plus 1 plus, and then each one of these terms in the first parenthesis are less than 1 over 2 squared. But now in the second parenthesis, then, well, each one of those terms is less than 1 over 4 squared. And we have 4 of them. So what we end up having is that we have 1 plus 1 plus 1 over 2 squared plus 1 over 2 squared. That's bounded by 1/2. And then we have 4 times 1 over 4 squared. So we end up with 1 over 4. So we can bound these partial sum by 1 plus 1 plus 1/2 plus 1/4. And if I continue this process, I'm going to be grouping things in a clever way. So I first take 2, then the next 2, then the next 4, then the next 8, then the next 16, and so on. So if I get the S2 to the K partial sum, I have this. Then this here is less than 1, the next term is less than 1. This first parenthesis here is less than 1/2, we already saw it. The next one is less than 1 over 2 squared. And then for the next one, we're going to have, if you look at it, if you count, we have k minus 2 to the k minus 1 terms. And each one of them is less than 1 over 2 to the k minus 1 squared. So that is just 1 over 2 to the k minus 1. So then when we put everything together, we end up that sk is less than 1 plus 1 plus 1/2 plus 1 over 4 plus dot 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 plus 1 over 2 to the k minus 1. That's pretty good. And now I can bound this by an infinite sum. So if I sum k terms and I sum infinitely many terms, obviously I'm adding more and more and more because all the terms are positive. And, well, this is our geometric series. This was the very first example that we saw. And that's nice because I know what the sum is. This is 1 plus 1 over 1 minus half. So this is 3. So I know now that s2 to the k is bounded by 3. So that subsequence of my partial sums is bounded by 3. Okay, now I know that I have a subsequence that is increasing and that is bounded. That subsequence converges. But how do I know that my whole sequence of partial sums converges? Well, we know by Bernoulli's inequality that k is less than 2 to the k for all k in the naturals. Okay? Well, and we know that my sequence of partial sums is strictly increasing. So sk is strictly less than s2k, which is less than 3. Oh, that's it. My sequence of partial sums is bounded. So the series 1 over n squared converges because remember the sequence of partial sums is increasing and bounded above, which means that it is convergent.